All right, so we're back here for the third video. Now this is the second part. We're going to do one more example here. This is number 11. So it says, find the area and perimeter of the figure. All right, so we have a figure here, A, B, C, D, F. That's a pentagon, though these are not the same lengths for that. And it is graphed on a coordinate plane. Now it's a little hard to see, but there's actually a grid. You can maybe see a little bit. There's a grid system set up here. So let's start with the area, okay? So we're going to find the area first. Now there's multiple ways that we can do this. Obviously, this figure is not a regular polygon where all the sides and all the angles are congruent. But what we can do is try to take this figure and divide it into a series of triangles, rectangles, trapezoids. So if we can get this into triangles and quadrilaterals, we can calculate the area. And so we're trying to cover up this whole figure. Let's break it into smaller pieces. Now there's more than one way that you can look at this, and the way that I do this might be different from the way you do it. So I would actually ask that you try this yourself and then pause the video, try it, and then unpause and see if we divide it the same way and if we end up getting the same answer. All right, now this is how I'm going to do this. Let's see, one thing that I notice is A and C are on the same vertical line here. I'm going to connect A and C. So I'm going to draw down here. And I see here's a triangle, and what I can do is make my height this horizontal line right here. Remember, for a triangle, we need to have a base and a height. They need to be perpendicular. So we have to create right angles here. I also see if I am here at point D, I can go across and create another right triangle from C to D to this point right here. Let's see, we could go, it looks like from point F, if we go across as well, that creates this right triangle here. And then what that leaves, I could actually stop at this point because this would be a trapezoid here. All right, so we can go ahead and find all these areas now. So let's take the triangle on the left here. And so triangle ABC, just going to draw an arrow down here. That's 1/2 the base times the height when we find the area of a triangle. Now in this case, the base and the height are the horizontal and the vertical. So the way that I've drawn it, the base is actually this length here. So I'm going to count from A to C. 1, 2, 3, 4, 5, 6, 7, 8, 9. So 1/2 times 9. The height going across is 1, 2, 3. And that's 27. Half of 27 is a decimal. I'm going to write that as 13.5. Okay, so there's one area there. Now this small triangle at the bottom, this is a height of 1. And this is a length of 1, 2, 3. So that triangle is 1/2 times 1 times 3, which is half of 3, 1.5. The triangle here at the top, that's 2, and then 1, 2, 3, 4. For the perpendicular, half times 2 times 4. 2 times 4 is 8. Half of 8 is equal to 4. And then the trapezoid here. So remember, a trapezoid is 1/2 times the height times the sum of the bases. The bases are the parallel sides. Now, in this case, that would be the 3 and the 4. We've already counted that out. Those are the bases. The height between them, I'm just going to count 1, 2, 3, 4, 5, 6. All right, and then this is 1/2 times 6 times 7. Half of 6 is 3. 3 times 7 is 21. All right, now if we want the area of the figure, area fig, we want to add up all the different smaller areas. Okay, notice that at this point, the way I've divided it, there are no empty spaces. We have calculated the area of each of these triangles. The triangles, they meet, they touch with the trapezoid, but they don't overlap. So I've covered the whole space with these figures. So we had 13.5 plus 1.5 plus 4 plus 21. And if we add those up, we get 40. And this would be units squared. So there's our area. That's our answer. But there are other ways to have done this. If you divided this differently, you may have, hopefully you also got 40. If you did, then what you did was correct. Now, one thing that I do want to tell you to be careful about, I would not have wanted to draw this all the way over to here. I wouldn't want to have a point that's not actually on the grid. This was somewhere between -2 and -3. I don't know where that is. I can't say that's -2.5. So that's when you're counting height, base, those things, you're perpendicular. You do need to be careful and make sure it's not a fraction distance, because then you're going to be wrong for that, or you're going to be off. So what we did was we calculated the insides. That inside triangle, this triangle was inside, inside, inside. Now you may find that difficult trying to find the right way to divide it up. So something else we could have done is we could have taken the outside. I'm going to take and draw a rectangle where the highest vertex, here is point C, that would be a horizontal. Now I'm going to go from the furthest left, which is B. The furthest right is D. Now I'm going to go down until I get to the lowest point, which was A. And here's my rectangle. The reason we might do that is because a rectangle is very easy to calculate. It's just base times height. And in this case, if I count across 1, 2, 3, 4, 5, 6, 7. So the base there is 7. And the height is, what I'll do here in terms of counting, this was -4, and this is +4. So 4 and 4. Actually, this is 5, sorry, up to 5. That's a total of 9. 4 spaces, 5 spaces, that's 9. So 7 times 9 is 63. And you're saying, wait a minute, that's not the answer, that's too much. And you're right. The reason it's too much is we have other areas here that are not part of the figure. So we're counting too much. But what we can do here is calculate these outside areas that we don't want. This one here is a triangle where this is 3. It's a right triangle. And this distance is 2 and 5 is 7. So 1/2 of 3 times 7. That is half of 21. This is 10.5. Down here, this is 2 spaces. And the perpendicular is 4 spaces. So half of 2 times 4 is 4. Up here, this triangle is 1, 2, 3, 4 spaces across, 2 down. That area will be half of 4 times 2, which is also 4. And then the last one here, now this is one that, let's see, how can I divide this up? Again, there's more than one way to do it. Let's see, that's -2, -3. I'm going to go like this. So I'm going to make a little trapezoid here. That's 1. And then this was 4. And this height is 1. So that would be half of the height times the sum of the bases, which is 5. So that's 5/2, which is 2.5. And then this triangle is 1 here. And 3 is 6. Half of 1 times 6 is 3. Okay, now you may say, well, that seems to be a lot more complicated. But let me show you what happens here. If we add all of the red areas, if we add up the red, 10.5 and 2.5 is 13. 17 plus 3 is 20 plus 4 is 24. Did I do that right? 13, 16, 20. Area of red is 24. And if I do 63 minus 24, oh, I get 39. Wait a minute. Let me make sure I didn't make a mistake here. Let's see, did I calculate correctly? I did not. Right here, that's 3. I apologize. So half of 2 times 3 is 3. Well, this is what happens, folks. We make mistakes, even the teachers. 63 minus 23. Well, look at that. It's 40. Okay, so I get the same answer by doing that. Now, again, you notice I have to be very careful with my counting because if I count wrong, then I make a mistake there. But that is 2 ways that I can come up with the same answer. So I can either do the interior and divide it up that way. If you'd rather draw a rectangle, and then this created a bunch of triangles, okay, in one trapezoid, I could calculate the outer area and then subtract that from the rectangle, and then what's left is the inside area. Okay, so that's finding area. Now, because I drew so much on there, I've got it again. Now we want to find the perimeter. That is the distance around. Okay, now again, there's a couple of ways that we can calculate perimeter. Unfortunately, we're not dealing with horizontal and vertical segments for the outside, for AF, for these segments. So I can't just count A to F diagonally. However, what we could do, I'll go back to the red here, I could think of this in terms of a triangle, where this distance here was 4, sorry, 1, 2, 3, and this is 1, 1, 2, 3, yep, and then 1. This would be easier if I could actually see my grid, but it's a little bit small for that. And if we do, I'll call that X right there. That's a right triangle. Well, we can do Pythagorean theorem, a squared plus b squared equals c squared, where my c, my hypotenuse, is going to be the slanted side. 3 squared plus 1 squared, and that's 9 plus 1 is 10. And then that distance, to take the square root of both sides, to undo the square, we square root it. So we get the square root of 10 is equal to c. Now that's going to be a decimal, but for now, what I'm going to do is just leave it as a square root. So we could go through and we could create these right triangles going around. And so if I want to find the length of AB, this was 2, this is 3, that's my A and B, A squared plus B squared equals C squared, and that's 4 plus 9 is 13. To solve it, we take the square root of both sides, so we get the square root of 13 is equal to C. So there's square root 13. Here is the square root of 10. Over here, that's 1. And then up, 1, 2, 3, 4, 5, 6. So the square root of, 1 squared plus 6 squared. That's 36 plus 1 is 37. So that's the square root of 37. As we move around. Okay, and then this is 2. 1, 2, 3, 4. The square root of 2 squared plus 4 squared is equal to c. And notice that what I'm doing here is I'm making a connection that at the very end of this, I'm going to square my legs and add them, but at the end I'm going to take the square root of that sum. So if you want to just go ahead and set it up here, you can. That's the square root of 4 plus 16, which is 20. So there's the square root of 20. And then the last one here, 3 spaces, and then this was 5, 6, 7. So the square root of 3 squared plus 7 squared, 9 plus 49, is 58. Now all of these are irrational numbers. They're not perfect squares. So we can either add them up as is. We have 1, 2, 3, 4, 5 sides. Or we can take the calculator and get a decimal approximation. In this case, I think it makes sense to do that. So I'll start with the square root of 58, and then add that. I'll just go around this way, the square root of 13, the square root of 10, adding these up, plus the square root of 37, plus the square root of 20. And what we get is 24.938. I'm going to go to 2 decimal places, so 24.94 for the perimeter. 24.94, whatever those units are. Okay? So you can use Pythagorean theorem. That forces you to do some drawing on this. There's one other way. We could do what's called the distance formula. D is equal to the square root of x2 minus x1 squared plus y2 minus y1 squared. Now you might be saying, if you've never seen this before, that's probably looking complicated, but let me show you what's happening here. Let's take this segment here. Let's take segment CD. We had 2 points. Point C was at -1, 5, okay, xy. And point D was at 3, 3. So we have -1, 5, and we have 3, 3. I'm going to label -1, 5 as my first x and my first y coordinate. And point D is my second x and my second y. And what I'm going to do is just substitute. D is for distance here, the lowercase d. So we take our x's and we subtract them. So I would take x sub 2, which is 3, minus x sub 1, which is -1, squared, plus y sub 2 is positive 3, minus y sub 1, which is 5, squared. And we'll simplify. This would become 4, because that becomes a positive. So 4 squared. This would be -2 squared. I'll keep that in parentheses. Now, one thing to notice here is that we have c equals the square root of 2 squared plus 4 squared. Notice we have the identical thing here. Now this one is negative, but we know that when we square a negative, we get a positive, -2 times -2. And so you end up with the same answer, the square root of 20. So the distance formula here is really the same thing as the Pythagorean theorem. If I think of, here's Pythagorean theorem, and if I take the square root of that, the square root of a squared plus b squared, well, here's my a, and here's my b. So if I know the coordinates, if I know the actual x and y values, this actually might be faster because you don't need to draw the triangles and count. But if you have it in the picture like this, graphed, I'm going to do it more visually. And that is the end of the notes.